Welcome back, students. In this video segment, we will cover one section, section 14.2, limits and continuity. And by limits and continuity, we're talking about functions of more than one variable. What we're going to do is spend most of our time talking about limits of functions of two variables, but this same concepts that I'm going to introduce to you work for functions of three or more variables. So before we dig into the concept of a limit of a function of more than one variable, we really should go back and take a look at what it means to have a limit of a function of just one variable from Calc 1. Okay, so let's do that. Let's do a kind of a really quick review of limits from Calc 1. Let's let f of x equal x squared. And let's consider the limit of f of x as x approaches 0 and what that means. Okay, in reviewing what that means, I'd like to take a look at the graph of the function. Okay, so let's take a look at the graph of y equals x squared. Very simple function. We almost grew up with this function. We've seen it so many times, the parabola. So here's f of x equals x squared. First of all, the limit of the function as x approaches 0 has nothing to do with the y value at x equals 0. What the limit is saying is as x gets infinitely close to 0, what are the functions, what are the function values doing? What are the y values doing? And we can see that as x approaches 0, let's say from the right-hand side, I'm indicating that with little arrows, as x approaches 0 from the right-hand side, the y values seem to be approaching 0. So the limit as x approaches 0 from the right-hand side, and we use a little plus in the exponent position to indicate that, the function approaches 0. The y values tend to 0. And similarly, as x approaches 0 from the left-hand side of the function, the y values also tend to approach 0. So as x gets close to 0, approaches 0 from either direction, the y values approach 0. So what we say is that the limit as x approaches 0 of f of x equals 0. So to sort of do a real quick recap of what I said in the last few seconds, the limit as x approaches 0 of f of x equals 0 since the function approaches 0 as x approaches 0 from every possible direction, either from the left or from the right. And this is how we evaluate limits, or this is how we think about limits. The limit of a function is saying as x approaches 0 in this case, the y values from either direction, the y values are tending toward or approaching 0. So let's take a look at another function. Let's let f of x equal, and let's let's change up our function above. We still want to keep part of our function. Let's let f of x equal x squared for, let's say, x less than 0, and let's say x plus 1 for x greater than 0. Okay, and let's take a look at the graph of that function, and we'll consider evaluating the limit as x approaches 0 of the function. Okay? See if you can anticipate what the limit's going to be ahead of time. Be kind of a good confidence builder if you can remember this stuff on your own. So let's take a look at the graph of the function. The function is the parabola as long as x is negative. So it's the same graph for x negative, except we're not including the origin here. So we put a little circle around the graph, and then we have the parabola to the left, y equals x squared. Then for x greater than 0, we have y equals x plus 1. Y equals x plus 1 is simply a line. So let's see. If we were allowed to let x equal 0, then y would equal 1. We're not allowed to let x equal 0, so there's a little circle there. If x equals 1, then y equals 2. And so our function looks like part of a line for x positive and part of a parabola for x negative. So let's see what happens with this limit. Let's see what happens as x approaches 0 through every possible direction. And it might seem silly for you to hear me say through every possible direction. Why don't I just say from the left and from the right? Well, my wording is chosen very, very carefully, and you'll see why in a few minutes. Let's let x approach 0 from the right. Let's let x approach 0 from the right. So as x approaches 0 from the right, we're looking at the limit as x approaches 0 from the right of the function. And that says we're looking at the limit as x approaches 0 from the right. As x approaches 0 from the right, x is always a little greater than 0. So if x is greater than 0, the function is y equals x plus 1. So as x approaches 0 from the right, x plus 1 approaches what? X plus 1 approaches 1. We can see that algebraically as x gets small but remains positive, x plus 1 approaches 1. So the limit as x approaches 0 from the right is 1. Notice that that limit didn't depend on the y value at x equals 0. In fact, there is no y value at x equals 0. The limit has nothing to do with the y value at the point at which you're evaluating the limit. Has nothing to do with the y value at x equals 0. There is no y value in the function at x equals 0. F of 0 doesn't exist. So let's see what happens as we allow x to approach 0 from the left. So as x approaches 0 from the left, that means that x is approaching 0 but staying negative. So as x approaches 0 from the left, we're looking at the limit. Well, as x approaches 0 from the left, that means x is always a little less than 0. And if x is less than 0, the y value is y equals x squared. And as x approaches 0 from the left, x squared approaches 0. We can see that from the graph, or we can imagine taking a small negative number. That means x approaching 0 from the left is a small negative, represents a small negative or small negative numbers. If you take a small negative number and square it, you get something that's still small. It's now positive, but it's still small. So the limit as x approaches 0 from the right and from the left give us two different values. So the limit, the plain old limit, the limit as x approaches 0, simply does not exist. So it was often said in Calculus 1 that the limit as x approaches 0, not from the right or from the left, that was called a two-sided limit. Two-sided limit. We called that a two-sided limit. Because x could approach 0 from either the right or the left. So if the two one-sided limits didn't exist in Calc 1, then the two-sided, if the two one-sided limits either didn't exist or existed and equal two different things, then we said that the general two-sided limit did not exist. So in order for a two-sided limit in Calc 1 to exist, we have to be able to approach whatever x value we're approaching from either direction, from every possible direction, and have the y values approach the same thing. So now let's consider, let's consider not in red, let's consider in black. Let's consider one more function. Let's let f of x equal the square root of x, and let's consider the limit as x approaches 0 of the function. Oops, I could have just said the function f of x. Okay. Well, this particular limit is often done incorrectly in Calc 1. In 30 years of teaching Calc 1, I've noticed that more than 50% of students will get this wrong. So here's the square root function. So Did you get the value of the limit? Can you think of the value of the limit? So here's the square root function. The mistake is to say that, oh, well, as x approaches 0, the square root approaches 0, or even worse, to substitute x equals 0 into the square root. We're never letting x equal 0. The limit has nothing to do with the function at 0. Nothing at all to do with the function at 0. So the most common mistake is to either plug in x equals 0 and get the square root of 0, which is 0, or to just notice that the y values seem to be getting very small as x approaches 0, so the limit should be 0. Both of those lines of reasoning are incorrect. The limit doesn't exist. We are not allowed to let x approach 0 from the left. X cannot approach 0 from the left. There's no function there. The domain of this function is all non-negative real numbers. So the limit as x approaches 0 from the left of f of x simply does not exist. That one-sided limit doesn't exist. So the two-sided limit can't possibly exist, even though as x approaches 0 from the right, the function y values do tend to 0. The limit as x approaches 0 from the right is the limit as x gets small of the square root of x, and as x gets small, the square root gets small. Okay, so the limit, the two-sided limit, does not exist. It plain old does not exist. So now we're going to move into our course. This was just a really quick review of what you spent 2 weeks to a month on in Calc 1 to bridge the gap from Calc 1 from algebra into Calc 1. That's the big bridge, is the concept of the limit, because everything in calculus depends on the limit. Everything meaning, for you guys, the two main processes or concepts of differentiation and integration. They're both limits, and we had nothing like it in algebra. Okay, well, that's not true. In algebra, sometimes we study, not sometimes, but in intermediate algebra, we studied logarithmic functions and exponential functions, and they have asymptotes, which are strictly defined using limits. But other than that, really, we don't see limits in algebra. Okay, even then, we never even bring up the name of a limit in algebra. So now consider a function of two variables. Let's let f of x and y equal x squared plus y squared, a paraboloid, circular paraboloid. And now that should be pretty obvious that this is a paraboloid. And I want to consider the limit as x and y approach 0 and 0. So as xy approaches the origin. So in this case, the variables x and y are approaching something. Okay, and I want to consider the limit of as the point xy approaches the origin of the function. Okay, so what does that mean graphically? So here's a graph of the paraboloid in 3 space, and what this means, what this limit as xy approaches the origin of the function x and y, is that if we have, and let me put a particular point xy in the xy plane. If this is a point in the xy plane, I want to let x and y approach the origin, but it has to be able to approach the origin along any possible path to the origin. Okay, so I've drawn a little point in quadrant 1, and xy is approaching 0, 0 means x and y, the point xy is approaching the origin along any path, any and every path that will take you from a point xy, from any point xy, to the origin. And there are a lot of paths that you can choose to get to the origin. Okay, there are a lot of points you can choose to get there too. So suppose we started with a point along the x-axis. Okay, that's a particular point that can be allowed to approach the origin. So if we take a typical point and let the point xy, in this case the point x0, approach the origin, this is the same as in Calc 1 letting x approach 0 through positive numbers. Or from the right, we could also let x approach 0 from the left. Okay, but we're talking about not just a single point, we're talking about the point xy. So we could place the point xy on the y-axis, in which case we'd be looking at something like 0, comma y, and we could let that point approach 0, the origin, okay, in which case y would be approaching 0 through positive numbers. We could start on the negative y-axis and then let that point approach the origin as y approaches 0 from the left. But those four directions are not the only directions or pathways to let x and y approach 0. We have to be able to take an arbitrary point, and I'm going to move it over just a little bit because my drawing is a little small. We have to be able to take an arbitrary point xy and allow it to approach the origin. So there's a point xy. I'm going to change the color here so it shows up. We have to allow x and y to approach the origin along any possible path, and the function has to approach the same thing in order for this limit to exist. So here's a path. I can think of a lot of paths that will approach the origin. As long as I take a path that eventually gets us really close to the infinitely close to the origin, I have to have the function values approaching the same thing. Okay? So as you're at some arbitrary point xy in the xy plane, the value of the function gets you to some point gets you to some point on the actual surface. So that would be in purple. That's the f of xy. So as xy it moves along that really weird red curve. I'll make the curve a little less bizarre. Let's get rid of that really bizarre curve. Let's do a little less bizarre curve. Let's say the x and y approach 0 along this sort of wavy curve. Okay, then above us, the z values on this surface will look like this, and I have to have those z values approach the same thing. Again, that little red curve that's approaching 0 is approaching 0 along an arbitrary curve from an arbitrary point in the domain of the function. And the domain of the function is the entire xy plane. The bottom line of all this is, for functions of one variable, we had to let x approach 0. We had to let x approach 0 through or whatever we're approaching through the only two possible directions, either from the right, from positive numbers, or negative numbers. For functions of more than one, or let's say two variables, I have to let the point xy approach whatever point we're approaching, the origin in this case, along any arbitrary curve. This is substantially different or more difficult than the function of one variable. For the function of one variable, there's two directions, from the left and from right. For functions of two variables, there are an infinite number of pathways along which I can approach, in this case, 0. Okay, so let's make this a little more clear. So my question I'm going to pose is, what is meant by the limit as the point xy approaches the point AB of f of x y equals L? What is meant by this? It looks like 2. I want it to be some L. What is meant by this? Okay. what is meant is, let me see if I can get a decent graph of what's going on here. Oops, that's not a good start. All right, maybe I should slow her down a little bit. Here's the first octant, and here's a surface in the first octant. Okay, so here's the surface z equals f of x, y. Okay, and here's the point. Let's say, let's do this in purple here. A over here, and then let's go over here to B. So here's the point AB. And above my point AB in the XY plane, make this pen a little lighter here. Above the point AB in the XY plane, I may or may not have a function value. Okay, so let's sort of identify, see if I can identify a point. Above the point AB, there may or may not be a function value there. There could be a hole in the graph. The AB doesn't have to be in the domain of the function. Okay. Okay, so what's meant by the limit as y approaches AB of f of x equals L is that z equals f of xy approaches the value of L as the point xy is allowed to approach the point AB along every possible path to the point AB. Okay, the point xy doesn't necessarily have to touch AB. In fact, this limit has nothing to do at all with what's happening to the function at the point AB. Nothing at all. It's saying that as that the z values can be made really, really, really close to L. The z values are getting extremely, extremely close. So here's the value L to L, as x and y are allowed to approach the point, as the point xy is allowed to approach the point AB along every possible pathway. So I'll indicate that by maybe putting in green here. Here's the point xy right there, and I have to allow allow myself to consider x and y approaching the point AB along every single pathway there, along every single pathway. The little green one is just one pathway. For emphasis, I could do a purple path that'll go this way a ways, and then finally zero in closer and closer and closer and closer to the point AB. The point is that I have an infinite number of directions along which I can approach the point AB. Oops. And in order to prove that the limit exists, I would have to show that the z values get very, very close to L along every possible pathway. Now, here's the deal. Not every limit exists. So how did we prove that a limit of a function of one variable didn't exist? All we have to do is to show that one of the two one-sided limits either doesn't exist, or that both of those two-sided limits have different values if they do exist. So the big point here is the exercises that you're going to be dealing with are ones in which you show that a limit doesn't exist. And to show that a limit doesn't exist, all you have to do is to find two pathways to the point that you're approaching, and it's usually the origin. You have to find two pathways, usually to the origin, where the z values are approaching different values. Okay. Okay. So let's do an actual example. I've done a lot of talking about it. Let's talk about a specific example. So here it is. So let's consider the limit as x and y, as x to the point xy approaches the origin of f of xy, where f of xy is the function, let's say, 3xy over x squared plus y squared. Okay. So what we have is this situation. We have a function in 3 space. We have a function in 3 space. My x-axis. Probably take that. Sorry. Let me do this one more time. I guess I could have done this off camera here to get this ready. We have some surface. We have some surface in 3 space. So I'm going to try to draw a sort of generic surface in 3 space. Okay. Here is some generic surface in 3 space. Sort of umbrella-looking shape. Okay. And I'm interested in evaluating or determining whether this limit as the point xy approaches the origin of the function exists. Okay. So I stopped the camera for a bit just to redraw the function with a little better perspective. So we're seeing sort of a function, some surface drawn where we can view the z-axis coming through the surface. It's not this particular surface. This particular surface probably looks very, very strange because at the origin the function doesn't even exist. But we'll use this to represent what's going on. So to determine whether this limit, to determine that this limit doesn't exist, what we need to do is find 2 pathways to the origin, because that's where we're letting x and y approach. We need to find 2 pathways to the origin along which we get different values for the limit. So the first thing you might want to try is to let x and y approach the origin along the x-axis. So I'm drawing in x and y approaching the origin along both directions of the x-axis. What's going on the curve is then in red, the z values may or may not be approaching a particular value. So as x and y approach the origin along the x-axis, the idea might be to figure out what's going on in red above the curve. Of course, it's not necessarily in red, but my drawing is. So let's call that path 1. So path number Roman numeral 1. So path 1. Let x and y, let the point xy approach the origin along the x-axis. The x-axis. Okay, so let's do that. Let's find the limit as x and y approach the origin, let's say along the x-axis. Along the x-axis of f of xy. Okay, well, let's pull this forward, push this forward a little bit. Along the x-axis, what does a typical point look like? It looks like x comma 0. So really, we're looking at, as x and y approaches 0 along the x-axis, we're looking at the limit as just x approaches 0 of f of x 0. x0 is representative of any point along the x-axis. I've drawn it on the positive x-axis, but it could be the negative x-axis. And let's see what that limit equals. This is the limit as x approaches 0, and let's find f of x comma 0. Well, f of xy is 3xy over x squared plus y squared, so f of x0 is 3 times x times 0 over x squared plus 0 squared. Okay, so look at what we did. We just transformed this limit of a function of two variables into an ordinary limit that we see in Calc 1. 3 times x times 0 is 0, so we're looking at the limit as x approaches 0 of 0 over x squared. And as long as I'm not letting x equal 0, and I'm not, the limit never allows x to equal 0. 0 over x squared is just 0. So as x approaches 0 of 0 is just 0. The limit of a constant is just that constant. Okay. So as x and y approach the origin along the x-axis, the z values, f of xy, approach the origin. So this is not the way I've got it drawn there, okay, that's okay. Next, let's try letting x and y approach the origin along another path. What's another simple path to approach the origin, along which we can approach the origin? Let's go along the y-axis. So there's path number 2. So path number 2, let the point xy approach the origin along the y-axis. Okay, well, what does a typical point look like on the y-axis? It has an x coordinate of 0 and some y value. So let's do this. Let's take the limit. Let's try to evaluate the limit as x and y approach the origin. Let's say along the, oops, not log, along the y-axis of f of xy. Now let's see what we get for that limit. This is the same thing as the limit. Well, as x and y are approaching the origin along the y-axis, the x value is always 0. So really, it's the limit as y approaches 0 of the function, but the function at 0, y. Okay, so let's see if we can evaluate that limit. This is the limit as y approaches 0 of, well, the function is of xy is 3 times x times y over x squared plus y squared. It's 3 times x times y over x squared plus y squared. So it's 3 times 0 times y over 0 squared plus y squared. So this is the limit as y approaches 0 of 3 times 0 times y is 0 over y squared. 0 over anything, any non-zero number squared, is just 0, and we have a limit of 0. So as x and y approach the origin along the y-axis, the z values above us, if you will, they approach 0. So far, it's looking like this limit, if it's going to have a value, should have a value of 0. Well, the idea in most of these problems you're going to work from this section is to show that a limit doesn't exist. So I need to look at another pathway to the origin. There are many different pathways to the origin. What would be another good one, but a very, very simple one? We could approach 0 along the x-axis, along the y-axis. We could also approach 0 along the curve or the line y equals x. I'm going to draw that line in purple. So here's the first octant. Here's the first octant zeroed in on. And here's the line y equals x. At least the line in the first quadrant. Here's y equals x. Okay. Of course, it extends past the origin into the third quadrant. So here's line y equals, a portion of the line y equals x in quadrant 3 in purple, and in quadrant 1. So let's for path number 3, is the, we'll call it the purple path, let's let x and y approach the origin along the line y equals x. So let's do it. Maybe I'll even stay in purple, so let's do path 3. Let x and y approach the origin along the line y equals x, and see what happens. Okay, well, let's do it. This is the limit as x and y approach the origin, let's say along y equals x of f of xy. Well, that means we're looking at the limit of, well, what does a typical value point look like along the along the line y equals x? It looks like the point x comma x, right? Along the line y equals x, along the line y equals x, y equals x. So the typical points are x and x, and then we let x approach 0. So let's see what we get. This is the limit as x approaches 0. Well, don't forget the function. The original function, just to have it here, was 3 times x times y over x squared plus y squared. This was our original function. Well, I want to find the limit of this function, but of x and x. So it's 3 times x over x squared plus, I'm letting y equal x, x squared. Or the limit as x approaches 0 of 3x squared over 2x squared. And those x squareds cancel. You can cancel x squares, you cancel common factors as long as you're not letting any of those factors make a 0 in the denominator of the fraction. And x is never equaling 0, x is approaching 0. So as x approaches 0 along the line y equals x, the z values approach 3/2. So this limit doesn't exist. We found 2 pathways along which we get different limits. Specifically along the x-axis we get 0. We also figured along the y-axis, but along the line y equals x we don't get 0, we get 3/2. Our conclusion, the limit as x and y approach the origin of the function simply does not exist. Okay. Alrighty, let's take a look at another example. This is an example that went fairly well. Sometimes when you evaluate the limit along the line y equals x, you still get the same limit, and we have to go further. So let's take a look at a case where we might have to do, we will have to do a bit more. So let's consider the limit as the point x and y approach the origin of f of x, y, where our new function is similar to our other function. It's another rational function of x and y. So it's 3x squared y over x to the 4th plus y squared. Okay. Make a little better y in there. Okay, clearly the value of the function at the origin doesn't exist. Okay, so this is a potential limit that might not exist. Okay, the value of the function doesn't exist at the origin, so we may or may not have a limit equaling or existing here. Okay, so let's do this. Let's try letting x and y approach 0 along the x-axis. So off to the side here, I'm going to draw just the xy plane to indicate the different pathways along which we can approach the origin. Let me move that down a little bit. In fact, let me move it over here. Okay, so first let's let x and y approach the origin. We're just looking at the xy plane along the x-axis. Okay, so let's say along the x-axis, let's find the limit as xy approaches the origin along the x-axis. Well, along the x-axis, y equals 0. So this is the limit as x approaches 0 of f of x comma 0. Or the limit as x approaches 0 of f of x0 is, just as before, we plug in x and 0, so it's 3 times x squared times 0 over x squared plus 0 squared. Or, and we're going to get something very similar to what we got in the last example. Limit as x approaches 0 of 0 over x squared. 0 over x squared is just 0. And the limit of 0 is 0. So that's a start. Okay, now let's come in toward the origin along the y-axis. So along the y-axis, let's do this again. Let's find the limit as x and y approach the origin along the y-axis of the function. Well, along the y-axis, x is always equal to 0. But y varies. But if we're approaching 0 along the y-axis, that means y should approach 0. So this is nothing more than the limit as y approaches 0 of f of 0y, an ordinary Calc 1 limit. So this is the limit as y approaches 0 of 3 times x squared, 0 squared times y over, and I think, did you catch a mistake in my previous limit? It's over x to the 4th. It doesn't change anything in terms of the value, but the algebra is not right. The power of x in the denominator is to the 4th power. So back to our current problem. X is 0, so 0 to the 4th plus y squared. So we're looking at the limit as y approaches 0 of 0 over y squared. 0 over anything except for 0. 0 over y squared is 0 as long as y is not 0, but we're finding the limit as y approaches 0, so it never equals 0. So it's kind of discouraging. We have the same values. Now let's do the same thing we did before. Let's let x and y approach the origin along the line y equals x. I'm going to bring down our little x and y axes. So that's our next pathway. Let's do this. Let's take a look along the line y equals x. Okay, so now along y equals x. Keep in mind, we're not looking at this in 3 space. We're only looking at the portion. We're looking straight down from space here into the xy plane. We're not looking at the actual surface graphed here. Okay, so let's do this. Let's continue on. We're going to evaluate the limit as the point xy approaches the origin, but we're going to restrict ourselves to being on the line y equals x. So along the line y equals x, I'm looking at f of x comma x. And then I let x approach 0 so that we have the point approaching 0, the origin. So this is the limit as x approaches 0 I already forgot what the function is. 3x squared y over x to the fourth plus y squared. 3x squared y, so 3x squared x over x to the fourth plus x squared. Okay, remember we're substituting y equals x. Okay, so this is the limit as x approaches 0 of 3x cubed over x to the fourth plus x squared. Okay, now I can simplify this rational expression. This is the limit as x approaches 0. I can factor out a x squared from the denominator and cancel two of the powers. Cancel that x squared with a factor of x squared in the numerator. So I'm really looking at 3x over x squared plus 1. Okay, again, I used the fact that x to the fourth plus x squared is x squared times x squared plus 1. And I canceled x squared with x squared in the numerator. Okay, so let x approach 0. As x approaches 0, 3 times x approaches 0 over 0 squared plus 1, and this is 0. This is disturbing. The z-values are approaching 0 along all three of these paths. What pathway am I going to try next? Maybe I'll try y equals 2x, y equals 3x, y equals negative 7x. What if I get all those limits equaling 0? Then I got a problem. So what I'm going to do is I'm going to use a little trick. I'm going to let x approach, I'm going to let x and y approach the origin along every line y equals mx. So what this is saying is I'm going to consider every single line except for one that approaches that passes through the origin. I want to let x and y approach 0 along almost every single line. Almost every single line. Almost every single line. I'm drawing a bunch of them. Okay, and I want to see all at once if I can figure out a different value, one of these lines that gives us a different limit. I'm letting x and y approach 0 along almost every line that goes to the origin. Which one's missing? Y equals mx. Y equals mx is an equation of every line that goes through the origin except for the y-axis. Every line that goes through the origin will have a slope except for the y-axis. Okay, and I already let x and y approach 0 along the y-axis. So let's see what happens if I evaluate the limit of this function as xy approaches the origin along any and every line y equals mx except for the y-axis, which we already figured out. Then we figured out that limit is 0. So let's do it. Let's take the limit as x and y approach the origin along the line y, along every possible line y equals mx of f of x, y. Well, that will be the limit. Well, that will be the limit of the value of the function at what point? Well, at the point x, and what's the y value? mx. So on a typical line over here, off to the side here, here's a red point, x comma mx. And I want to let that point approach the origin. So if that happens, that means that x should approach 0. So this is the limit as x approaches 0 of 3x squared y, 3x squared times y, y equals mx, over x to the fourth, x to the fourth, plus y squared. The y equals mx, so mx quantity squared. Okay. All right, so let's do this. I want to make sure that I got the right button. 3x squared y over x 4 plus y squared. Okay, fine. Okay, so this is the limit as x approaches 0 of 3mx cubed over x to the 4th plus m squared x squared, where m is just a fixed slope of a typical line. Okay. Limit x approaches 0. I'm going to factor in x squared from the denominator. Okay, if I do that, then I can cancel out a factor of x squared. Since I'm never letting x equal 0, I'm letting x approach 0, but never touch it. I can cancel the x squared. We're getting down to the end of this particular path. So as x approaches 0, what does 3 times m times x squared approach? It approaches 0 over 0 squared plus m squared, or 0. It looks like this limit should have a value of 0. There is no other line along which I can approach that I can approach 0 there's no other line left to approach 0. I've drawn a few of them, maybe 8 or 10 or 12 of them or whatever, but they really fill up the xy plane. Is there any other way we can approach 0? Yes. The origin, yes. Let's approach the origin along a different curve. Let's try approaching the origin along the curve, and the simplest curve, next curve you can think of besides y, a line. So let's try along y equals x squared. And you might think, we can't get anything different. Although as you approach the origin along every one of those lines, the z values are approaching 0. And y equals x squared just fits into those, is squeezed into those lines, and so it seems like the z values should approach 0. Well, let's see. Let's take the limit as x and y approach the origin along the parabola y equals x squared, and see what happens. Okay, well, this is the limit of f of x, comma, well, what's the y value on y equals x squared? It's x squared. And then let x approach 0. So we're doing this now. In the xy plane, remember, we're not looking in 3 space, we're only looking at in the domain area of this function in the xy plane. We're letting x and y approach the origin along the curve y equals x squared. And we want to see if we're going to get something different than we got before, different than 0. So this is the limit as x approaches 0. The function was, see, 3x squared y, so 3x squared y equals x squared over x to the 4th plus y squared plus y, which is x squared squared. So this is the limit as x approaches 0 of 3x to the 4th over x to the 4th plus x to the 4th, or the limit as x approaches 0 of 3x to the 4th over 2x to the 4th. Oh my goodness. I can cancel out those powers of x to the 4th since I'm never letting x equal 0, I'm just letting x approach 0. And we get something that's completely counterintuitive for a lot of people. As I allow x and y to approach the origin along the curve y equals x squared, the z values, they approach 3 halves. although as if I approach the origin along any other line, here's the other line, here are a few of the other lines in red, as I let x and y approach the origin along any of those lines, the z-values approach 0. But if I jump to on the parabola and let x and y approach 0 that way, the z-values, they jump to 3/2. They stay at 3/2, but in fact. How can that be? How can that be? Well, I'll give you an idea of how that can be, but I want to conclude the problem. So the limit as x and y approach the origin of f of x and y does not exist. We get two pathways, any one of those lines, and along the parabola we get different. We get a different limit value. Okay, so why is that true? How can that possibly be true? Here's an explanation of that. Let me attempt to draw a few of those lines that are approaching the origin. So here's one. Let's see if I can do this. Here's one line. Here's another line. Oops. I guess it's going to make me do a fresh line every time. Give me a minute here. Here are a few of the lines that are approaching the origin. A few of the lines on y equals x. I want a few more. Bear with me. Just sort of randomly drawing. Oops, that one doesn't even go through the origin. I should probably cut my losses here. Got two of them that don't even look like they're approaching the origin. Get rid of that one. Okay. Here are a bunch of lines that approach the origin. Now, here is the parabola y equals x squared in red. Ooh, my goodness, let me redraw it. I'm doing this freehand. That's good enough. Here's y equals x squared. Okay. So, along y equals x squared, in fact, the z-value is always 3/2. The x to the fourth canceled out, so the z-value along the parabola is always 3/2. So at this point right here, at this point right there on the parabola, z equals 3/2. So now let's assume we're at that point that I've just identified, right there on the graph. And let's approach the origin along the line that intersects that parabola there. Okay. If you missed what I just said, see that point where I've just drawn the intersection. Let's let x and y approach 0 along that line. What's going to happen to the z-values? We already figured it out. The z-values approach 0. Okay. Let's jump to a different line. Let's jump to the next line where that intersects that parabola right here. What's the z-value right there? The z-value is 3/2. But if I start at that point and stay on the line and approach 0, approach 0 along the line, the z-values approach 0. Remember, no matter what line I'm on, y equals mx, the z-values will approach 0. I just proved that. Let's jump to the next one. At that next point, z equals 3/2. Along every point on this parabola, along every x and y value on this parabola, the z-value equals 3/2. But if I from that point where z equals 3/2, I decide to stay on a line and approach the origin, the z-values approach 0. Now, change your perspective. Let's go back to the original point where z equals 1/2 above, on the top, the highest one here. Now let's stay on the parabola and approach the origin. So I'm going to do a little red arrow along the parabola. As I approach the origin and stay on the parabola, z value equals 1/2, z value equals 1/2, z value equals 1/2, z value equals 1/2, 1/2, 1/2, no matter what. As long as I stay on the parabola, the z value is 1/2. But the x and y are approaching 0 along that red parabola, but the z value is staying at 1/2. But it's as soon as I decide to take a point on a particular point on that parabola, as soon as I decide to take a particular point on the parabola, and instead of staying on the parabola, I move to the line and approach the origin, the z values approach 0. Okay. I'm hoping this little explanation works. This explanation does not appear in the textbook. It's very difficult to actually draw these functions. In fact, it's impossible for me to draw these functions where the limits are 0 along. The limit is 0 along every possible line, except and when you go to a simple other curve like y equals x squared, the limit is not 0 anymore. Very, very difficult, impossible for me to draw. In any case, it's not essential that you're able to see the calculus that's going on visually. What's important is that you realize that if you're trying to show that a limit doesn't exist, you have to find two pathways along which the limit values give you the limit is equal to two different values. Just like approaching right, 0 from the right and 0 from the left in Calc 1 and getting two different limit values. Okay, then the limit doesn't exist. So typically what I did is what you might want to consider doing. First try along the x-axis. I'll keep in purple. So let's say xy approaches the origin. So different paths. What should you choose for paths? Paths for xy approaching 0, the origin. So maybe try along the x-axis, along the y-axis, along the y and y equals x. Then if you still get the same limit, try y equals mx. Try every line through the origin except for the x-axis. Okay. Then maybe consider y equals x squared. Well, what if you get the same limit again? Maybe try y equals x cubed. What if we get the same limit still? Well, maybe try y equals the square root of x. Okay, etc. Try simple curves that approach the origin until you find a limit that is different from the previous limits. Okay. Okay, that's the bulk of this section. There are simple limits. In fact, before I go there, I said y equals the square root of x. You might want to write that a little differently. Maybe x equals y squared, then x equals y cubed, etc. That's a little better way to think about it. Okay, there are some limits that are simple to evaluate. They don't happen very often because the point is to consider limits that don't exist. But if you had to, for example, figure out the limit as x and y, let's say approach, I don't know, let's say the point 1, 3 of 4x squared times y squared minus 2x. Okay, this limit is pretty clearly exists as x approaches 1, 4x squared, and 2x. They approach 4 and 2, and as y approaches 3, y squared approaches 9. The limit laws from Calc 1 still hold. The limit laws from I think section 2.3, but I can't remember from Calc 1. I should. I've been teaching the Calc 1s like forever. The limit laws from Calc 1 still hold true. So if this limit exists, you can use those limit laws. In particular, this limit becomes the limit of 4x times the limit of y squared minus 2x, as long as the limits exist. And this is the limit of x squared, and you can distribute limits. This is one of the limit laws, y squared minus the limit of 2x. So as for 4x squared, as x and y approaches 1 and 3, x is approaching 1. Okay, and for the other, the next limit in the product, we're still looking at x and y approaching 1 and 3. So this is the limit as x approaches 1. And limit of y squared is now the limit as y approaches 3, since it's independent of x. And the limit of 2x is the limit as x approaches 1. And we simply get 4 times 3 squared minus, as x approaches 1, 2x approaches 2. Or 4 times 9 minus 2, or 4 times 7, or 28. Okay, so there are some easy limits. They just don't happen too often. The idea is to be able to figure out that a limit doesn't exist. The other thing that's discussed in this section, the only other thing, is continuity. And while continuity holds together a whole lot of your calculus, in fact, it holds together pretty much all your integration theory for our course, because a sufficient condition for the integral to exist is that we look at continuous functions. We say that f of x from Calc 1 is continuous at x equals a if the limit of the function exists, but it also has to equal f of a, that the y values on the function are actually approaching the y value that's actually there at f of a. So similarly, for functions of 2 variables, and this extends to functions of any number of variables, f of x is continuous at ab if the limit as x and y approach the point AB of f of x and y equals the actual z value that's at the point AB. Okay, now this idea holds together a lot of multivariable calculus, the calculus we're studying, but for us, we generally assume that we're working with continuous functions, so we don't have to spend too much time looking at that definition. Okay, and that ends this section. I recommend that you get started on homework for section 14.2 as soon as you possibly can, and I'm looking forward to talking with all of you guys again soon.